Good afternoon, and welcome to the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, and the Near Shoemaker Descent to Eros press briefing. I'm D.W. Reese, Head of APL Public Affairs. As you know, Monday was an incredible, successful day for the Near mission and the Discovery program. Today, our panelists from NASA and the Near team will discuss the mission and details of Monday's descent. Introducing our panelists from left to right, we have Dr. Jay Bergstrahl, Acting Director, Solar System Exploration from NASA Headquarters. Dr. Bob Farquhar, Near Mission Director from Johns Hopkins Applied Physics Laboratory. Dr. Bobby Williams, Near Navigation from NASA's Jet Propulsion Laboratory. Dr. Joseph Ververka, Near Imaging Team Leader from Cornell University, and Mr. Tom Coughlin, Near Project Manager from Johns Hopkins Applied Physics Laboratory. Our panelists will begin with some remarks, and then we will open it up for questions. Dr. Bergstrahl, we'll begin with you.
Thank you. As Denise said, and as you all know, the near touchdown on Eros on Monday was highly successful. In fact, it was so successful that not only did the spacecraft survive, it's evidently intact, but we have remained in regular communication with it. This is successful, I think, beyond our highest expectations. NASA intends to take advantage of this success by extending the mission up to 10 days. To gather data from the gamma ray spectrometer experiment on the spacecraft. As I say, we have been in communication with the spacecraft. The gamma ray spectrometer's operation is being tested even as we speak, and pending confirmation that the instrument is working properly. We will extend the operation 10 days to gather further data on the abundances of elements present in the surface of the asteroid. These measurements have the potential of improving the precision of our knowledge of these abundances by up to a factor of 10. And this is important in the context of understanding the relationship between asteroids, this asteroid particularly, and the collection of meteorites that we have on Earth, which are can be thought of as returned samples of asteroids. We see from remote sensing of asteroids of some, and the properties of some of the meteorites that we have in the collection. Sort of the holy grail here is to nail down the connection, at least between one asteroid and one family of meteorites. And this, in turn, bears very importantly on our understanding of how the solar system began, the physical processes that formed our solar system as it is today. We're very excited by this and look forward to seeing the results in a few days. Thank you.
Well, let's see. I've been doing pretty good this week. Everybody on the team has been feeling quite well. Well, it's been a good week. I don't see how it can get much better, actually. But as you heard, we might be doing a few more things, which we never planned on doing. One of the questions that has come up over the last week or so is people have asked me, well, why didn't you land this thing on February 14th, which is Valentine's Day? Why did you do it on February 12th? Well, 12 is my lucky number. But more than that, I've been telling everybody that we probably have a less than 1% chance that the spacecraft would survive the landing, but I left a couple more days that we could get tracking so we could confirm that we could get signals back. So you see, I was a little more optimistic than I let on, I have to admit. We've had a number of firsts on the Near mission, and if I could have the first visual, this just lists a number of them. The top three, of course, are the first encounter with a C-class asteroid. That was done back in 1997 with the asteroid Matilda, a rather large asteroid in the main belt. Then we were the first spacecraft to orbit a small body, and now we are the first spacecraft to land on a small body. Now, if I could have the next visual, to put this thing in some context, there's been various planetary orbiters that have been first to a particular body. Of course, we all know about Sputnik 1 is the first one to orbit the Earth back in '57. And then we have Luna 10 that went to the moon. That was quite a while ago. And then our first spacecraft, the first U.S. spacecraft to orbit another body, this is Mars, was Mariner 9. And finally, last Valentine's Day on February 14th, the Near Shoemaker spacecraft was the first spacecraft to orbit a small body when it was placed into orbit around Eros. Now, if I can have the next visual, I'm very proud of the fact that we are now the first lander on a small body. And you can see that there are only 3 other spacecraft that have this distinction of being the first to a particular body, and they're all Russian spacecraft. They were first to the moon, Venus, and Mars, although we came there later with other landers. But this is the first U.S. spacecraft to land on a solar system body, and the first one to land on any small body, and this was, of course, the asteroid Eros. Well, let's see, I want to say that you've also heard in a lot of news reports that we were going to do a controlled crash. This was not a crash. This was a soft landing. As a matter of fact, it's a very soft landing, maybe the softest of all time, because we landed at an impact speed between 1.5 and 1.8 meters per second, which is less than 4 miles per hour. Other spacecraft that have landed, like Viking, landed at 2.4 meters per second. Of course, they had a landing gear on. Then there's Surveyor that landed on the moon, that landed at 3 meters per second. And then if you go to things like Mars 3, that landed at almost 21 meters per second, and it still survived. Well, ours is surviving, and it's actually sending back housekeeping data right now, but we hope to get some science data in the next few days. Today we have our last scheduled track, which is going on right now at the Goldstone Deep Space Network. Now, obviously, all this was a big team effort, and there was an awful lot of people involved. And some of them are right here on this panel, of course, and we never would have gotten to this point. One man in particular, and his systems engineer, the man sitting at the end of the table here, the project manager, Tom Coughlin, I don't think anybody else could have done this job in 26 months. I've told him that several times. I hope I'm not embarrassing him now. And Andy Santo, who is our main systems engineer prior to launch, he also did a heck of a job, and there was a lot of other people involved, a lot of other subsystems engineers. On the mission design team, mainly it's Dave Dunham and Jim McAdams, and we had a whole mission operations team, and they obviously did a great job on February 12th, well beyond normal operations. We also have here, we brought out part of the navigation team from the Jet Propulsion Laboratory. The leader of that team is sitting right next to me, Bobby Williams, and the rest of the team is in the audience out there. And if you could stand up, please. Yeah, go ahead, stand up. Oh, there's only 3 of them here, but there's other ones back at the Jet Propulsion Laboratory. We also have a good team from the Jet Propulsion Lab as far as DSN, and Al Berman was our main representative there. So with that, I've given enough credits. I'll turn it over to Bobby Williams to tell you about how they navigated this thing, which is a feat unparalleled in space history.
Okay, thank you, Bob. The secret to success here, I think, was that we did our homework several times. The people working on the project, NAV, who you've seen some here. We also have several people back at JPL who are probably watching this. Say hello to. I don't want to mention each name because I'll forget one. But there were several challenges to this as opposed to a planetary lander. The biggest being that we had to change mathematical models that as we get close to an irregularly shaped body like this, it's not like getting close to Mars or the moon. We actually had to change the way we modeled things that were going on. So we were trying something that untried in the history of deep space navigation. We got our verification on Monday that we did our homework right, and the models worked out the way we thought. If I could have the first slide. This slide indicates the last 47 minutes of the trajectory. This plan was actually developed over the course of 2 years. We started 2 years ago. The original landing site has moved from the South Pole down to its current location of Eros, mainly because we fed back and forth with the science team their desire for pictures and the place they wanted to take pictures, and our desire to have a simple dynamic situation that we could deal with the landing situation is an open loop control in the parlance of engineering. We don't have any feedback on the burns. Once we start doing the burns, it essentially occurs in a time sequence. And so to model this nominal trajectory, we had to look at dispersions around it, which I'll get to in a minute, due to uncertainties in each maneuver as it happened, and our uncertainty in the trajectory itself, knowing where we are in position and velocity at any time. So from this, you can see these last 4 burns, numbered on this plot, EMM 2 through 5, were the final deceleration or burns that we did after we had bumped out of orbit. We're actually landing in the opposite direction of the rotation of Eros, which in itself makes things a little bit tricky. We have high relative motion over the surface, and that had to be canceled along with coming down vertically. So you can see the sequence of burns. We designed them. Originally, we only had 4 burns, our goal being to maximize time at altitude for taking pictures, but not necessarily optimizing for impact velocity. We added the 5th burn to minimize the impact velocity as much as we could. So if I could have the next slide, shows our pre-landing determination of what the possibilities were for radial landing velocity. This is based on a analysis called Monte Carlo analysis, where we randomly drew samples and projected each one of those to the surface and see what the predicted impact velocity was. And as I said, of course, we're doing all this with untried, untested mathematical models. And as you can see on this plot, all the radial velocities were predicted by our models to be less than 3 meters per second, even at the worst. The higher bars on this chart indicate a higher probability of being at that velocity. So in effect, the final landing velocity, we believe, based on a preliminary analysis, and we'll have time to fit data and actually come up with a more precise number later, but right now we're estimating 1.5 to 1.8 meters per second at impact, which is in the low part of this curve, which indicates that it was a very low probability of that occurring. So I think the good Lord smiled on us on that day when we landed, that we actually didn't land in the most probable velocity. Okay, the other interesting velocity to look at is the transverse velocity, which we had to cancel, as I mentioned, on approach. If I could have the next slide. Okay, the transverse velocity, you can see it's a much broader peak, and this would be the sliding motion. As the spacecraft hit the surface, it would be sliding sideways or forward. And we believe, again, based on our preliminary analysis, that transverse velocities are somewhere in the 0.2 to 0.4 meter per second range. So it's a very slow, that's 20 centimeters per second to 40 centimeters per second. And the spacecraft was able to thrust and contain that without flipping over on its side or something. And finally, if I could have the last slide, please. This shows, again, a pre-landing estimate of where our random samples would land and the dispersion of those samples in latitude and longitude. And it's superimposed on a picture taken much earlier at a higher altitude. But mainly we wanted to see kind of the terrain we were dealing with, and to be sure that we didn't land in a crater or something bad like that where it would be in shadow. The three arrows indicate three different designs that we had. Again, with the 4 burns or the 5 burns, you can see they're all very close. In the lower left corner of that picture is an indication of what one 100-meter square would look like on the surface, just for scale. So you can see the total dispersion in latitude and longitude is about 1 kilometer or less. We now believe, again, from tracking the Doppler signal that we've been monitoring since impact and through the impact, actually, we believe that the actual landing occurred in the upper right-hand corner of that picture. From the Doppler residuals, we've also determined that the landing time, at least the first indication of a landing time, was at 2000 hours, 1 minute and 52 seconds UTC. And there's some interesting effects in the Doppler before that would indicate that there's some kind of a ground effect as we got low. So for a spacecraft that is not built to land, this came off extraordinarily well, and I think it's a testimony to the hard work put in by both the people at APL building the spacecraft and controlling it, and the JPL navigation team. So with that, turn it over to Dr. Baburka.
Thank you, Bobby. A major goal, probably the major scientific goal of the descent to the surface of Eros was to obtain high-resolution images, in fact, images at an unprecedented resolution of any asteroid surface. And it's a real pleasure to be here on behalf of the Near Imaging team to share with you some of the results of that descent. We could begin with the first graphic, which illustrates the chosen descent area in a large depression about 10 kilometers across called Eros on Eros. And I think, as everyone knows, the descent to the surface was extremely successful. We were hoping that we would get at least 40 images on the way down. In fact, we got 69 images, roughly from an altitude about 5 kilometers, where you can see detail as fine as 1 meter or 3 feet across, down to the very last image at a resolution of 1 centimeter or so, from an altitude of less than 400 feet or about 125 meters. Some of these images have been released, were released on Monday. The next graphic just reminds us of 4 of those very high resolution images we released, including the one which is at the bottom right, which is the last image returned. And in a few minutes, I will sort of try to tell you what it is that we are gleaning from these special views of the surface of Eros. But to begin, let's start at about a 5-kilometer altitude and work our way down to the surface. The next graphic will show us a typical view from an altitude at about 5 kilometers. And here you can see detail which is, about the size, a little bit less than 1 meter across, maybe 2 feet across. For reference, there's a large boulder at the bottom, which is probably 35 meters across. And the striking feature is that the surface looks very, very subdued. Notice the total absence of small, fresh craters. Even the large craters that you see, some of which are 30 to 50 meter across, are kind of hard to see because they're very, very subdued. And it looks very much like a surface where material has been imported, probably ejecta from other impacts on the Eros possibly, that has brought in some of the very coarse materials, some of the large boulders you see, in addition to some finer material, which is responsible in large part probably for subduing the topography of this surface. As we get closer to the surface, next step, please, our resolution improves, and also the lighting starts to improve in a sense that the shadows become slightly more visible, which is helpful in trying to see features on the surface. Here we're actually crossing into the Eros depression. The time sequence is from the upper right to the lower left, and a geologist can notice that there are slight changes in the character of the surface as we move down into Eros. Again, everything is very subdued. The craters are difficult to see. Some of the largest boulders, for example, there's one near the upper right, which is about 10 meters across for scale, They're all there, but there's a slight transition of the character. There are more boulders. The surface is slightly rougher as we go down towards the lower left into Hemorrhoes. So things are changing as we get down into the Hemorrhoes Depression. And of course, as we get closer to the surface, the resolution gets better still. And the next step, please, gives us an example of a close-up of one of the boulders that we saw on the way in. And there's a special reason I'm going to show you this boulder because, as you notice, it's the boulder at the upper left. There is a blow-up in the center. The scale applies to the blow-up. The boulder is about 10 meters across, 5 meters wide. And notice that on impact to the surface, it's apparently cracked into at least 6 different pieces. And what is significant is to remember that the size of the Near spacecraft, which is currently sitting on the surface, is about half the size of half of that boulder. So in fact, our camera, even at this range of about 700 meters from the surface or so, is able to resolve the detail that would show the spacecraft sitting on the surface of Eros. Let's continue our descent to the surface and see what we see. Now we're only about 700 meters above the surface of Eros, and we can begin to see things in great detail. Some of the finer boulders that you see are only the size of a baseball across. The prominent large boulder at the upper edge of the image is only 10 meters across. And we begin to see something very interesting. Again, just notice that there are no small fresh craters, but there are differences in texture of the surface. Near the middle of this mosaic is an unusually flat area. And one of the mysteries that we were trying to solve in this descent was to understand some of these flattish areas that we have been seeing in some of the late orbital images. And so I'm going to step back in time just to show you an example of a very intriguing set of images that we obtained late in January. And if we could have the next time step. Here, the resolution is a little bit coarser than what we have been used to, but still we can see detail, probably at the scale of a few meters or so, or a little bit better. In the lower part of the picture is a crater that is about the size of a football field, but the remarkable thing about it is its floor has been covered by a very smooth deposit. Near the upper end of the picture are some more smooth deposits. And one of the things we noticed is that there's some process on this asteroid that we don't understand that seems to sort out the fine particles from the regolith and move them somehow into the low-lying areas. We were hoping that the very high-resolution images at descent would help us understand this process. And as our last 2 slides will show, actually we were very fortunate so that we got some clues, but as often happens with the clues came some additional mysteries. So let's look at the last 2 images that were obtained on the way down. This is the next to last image that was obtained on the descent to the surface. From an altitude of about 220 meters. And now some of the prominent boulders and pebbles can be seen down to a scale of things the size of a golf ball. The arrow points to a particular boulder that we'll use as a marker, which is about the size of a large cantaloupe or a cranshaw melon for reference. We can see things at the scale of an inch or so. But what is remarkable is in the lower left-hand corner, near where the arrow is a transition from the rougher terrain in the upper half of the image to some of these smoother areas that have intrigued us so much. And as we go to the last image obtained by Near, we can see now the arrow points to the same cantaloupe-sized rock that we were looking at before. And now we see what one of these flat areas looks like close up. And the mysteries continue because not only do we still see that these deposits are extremely flat, but in addition to being covered in places by boulders, such as the one indicated by the arrow, right below the boulder is an intriguing feature. There is a close-up of it in the upper left of the frame, and it looks very much, in terms of scale and everything else, as if you came down to the surface of Eros And in this flat area, which apparently we think may be made of some very loose, fine material, you extended your arms, stretched out your fingers, and just pressed your hand into the surface of Eros, making a depression about an inch deep. There is a similar depression that's a little bit to the right of the arrow that's shown in the upper right in detail, and that's about the size of a footprint. So there's some process in these areas that's not only sorting out apparently fine material, moving them in these deposits, but depositing them in layers, and then something comes along and makes the layers collapse. Now, what is going on is a tremendous puzzle, especially since we are dealing with a body which doesn't have an atmosphere and doesn't have any water. As you may have noticed from the press release, this last image of Eros was not fully played back. The bottom part of the image was transmitted by the spacecraft, but at that time the spacecraft was no longer pointed at the Earth, the antenna was no longer pointed at the Earth, so the rest of that image, which may contain the explanation to this mystery, was beamed off into space, probably in the direction of some distant star like Alpha Centauri, and 4.3 years from now, the Centaurians will be able to receive the data and find out what is going on. For us, it does remain a mystery. The other thing to kind of realize is that this is an extremely detailed view of the surface of Eros. Those of you in the audience here have been looking at a large screen, and it's important to note that the size of that last image we received actually is smaller than its projection on the screen that you were looking at. So we really have seen Eros in great detail. And that has allowed us, of course, to answer a few of the questions we have had, but having answered a few questions, these images have presented us with a bag full of mysteries that will keep us scratching our heads for years to come. And I think in closing, I just want to emphasize that scientifically, the NEAR mission has been a tremendous success because in addition to these high-resolution views, we have, in fact, over the last year succeeded in a global characterization of the asteroid. I'm holding in my hand a model of the asteroid to sort of illustrate that we now know globally what Eros is like. But more importantly than that, these descent images we just talked about have shown us part of the surface in detail sufficient to resolve objects the size that I have in my hand. But that's actually an understatement because the very few last images have actually been able to resolve the kinds of dents on this model. So this has been a tremendously successful mission, and some of the big questions have been answered, but fortunately many mysteries remain, and that is the whole point of exploration and discovery. And with that, I'd like to pass the discussion over to the person who is largely responsible for making this happen, our project manager, Mr. Tom Coughlin.
Well, I'd like to switch gears a little bit and talk about the 7 years prior to Monday. There were 7 years, as Bob had mentioned. We took 24 months from the time NASA told us to go ahead to delivering it to Cape Canaveral, 26 months to launch. Then we were in cruise for 4 years, getting out to Eros, and a very successful year at the asteroid, where we accomplished 10 times the data that we anticipated in the launch of a Near Shoemaker spacecraft. Why did this happen? I've asked myself that several times recently, and it starts with the NASA trust in the Applied Physics Laboratory, and that trust was unwavering. We had some low times as well as we are celebrating one of the high times today, but if you remember back in December of '98, we lost a spacecraft for a couple hours. We had a burn anomaly as we were getting ready to go into orbit around Eros. In January of '99, we were due to go into orbit. And throughout those low days around here, NASA was never here. What went wrong? What went wrong? All they kept doing from the top down is calling us, what do you guys need? What do you want? How can we help? And what we did as a team is try to permeate that thought process over to all our suppliers, hardware suppliers, the science team. And I'll go through briefly just a couple examples of that. We had a science team that came on board about a year after we were into development. So this wasn't the PI mode, principal investigator. mode that is used on Discovery today, these scientists had to come in and work with instruments that we were developing in conjunction with industry, other government agencies, other universities. And that was my biggest concerns. Oh God, here comes the science team. Well, that concern never materialized. These guys came in, worked with our engineers that had developed these, or in the process of developing these instruments, where they could offer suggestions that we had the time to implement. We did so, but they also were willing to take the word no and find a way to work around what they considered a shortcoming. Then I go out to JPL. I thought Bob and Bobby here were joined at the hip. I really did. And the team, they just worked wonderfully with us. And that's throughout the 2 years of development, planning on how we were going to get there. And NAV wanted, of course, accelerometers that we couldn't purchase and other parts of the spacecraft that we couldn't accomplish. But they also learned to work with what we did have and worked very well with it. Then I'll just make a general statement about our hardware suppliers. As I said, we tried to pass this trust on to them that was so generously given to us by NASA. And in so doing, every instrument, every piece of hardware was delivered on time. And it worked. And what does that all say? I think we've been able to demonstrate that better, faster, cheaper, with better being first, can work, does work. And I think we're proof of that. But again, I say the emphasis has to be on better. You have to think smart and be willing to think out of the box. Don't go back to your old tried and true methods of doing things. And on that note, I think I'll close.
Thank you, Tom, and panelists. I'll now open it up for questions here in the auditorium, and then if we get some questions and phone in, I'll go to those. Christy Marin and Mike Buckley from APL Public Affairs will bring you a microphone. If you would please state your name and affiliation and then your question, I appreciate that. Leonard? Oops, sorry. Leonard?
Leonard David with Space.com. Maybe for Bob. Spacecraft, as far as the landing area itself, are you expecting the spacecraft to live beyond the 10 days, or what's the projection of how long it would survive?
We think, we just did some calculations on that. We weren't too worried about that up to now. As a matter of fact, I'm surprised we're still talking about this thing. But we think the Ides of March might be kind of bad for the spacecraft. The sun's getting kind of low at that point. We're starting to get shadows and so forth. But I guess the sun won't really set until about April 2nd in the area that we're in.
No interest in NASA, Dr. Bergstrahl, of funding it beyond the 10 days if it's still in great shape?
We're looking for science, and our indications from the science team here is that they can accomplish what they need to do in about 10 days.
Yes. Gentleman red. Chrissy, you're on the right.
Bob Zimmerman. I'm here for Astronomy and the Sciences magazine. On Monday, there was some conversation about the landing, the spacecraft having bounced when it hit. I would be curious if you can give some details about the actual sequence of impact, what it was like. Besides the speeds, do you think there was a bounce, and what orientation is the spacecraft now sitting in, and is there any damage to solar panels, to anything at all that you can get?
Okay, I'll take that one. Yeah, the indications of bouncing, we initially were looking for a bounce, really, because we knew that we had touched down before the last burn had completed, and so it had time to go. So we were assuming, and it turned out, I think we were wrong, that it would rise back up and then fall again. What actually happened, and we have confirmation of this from the Doppler tracking from the Deep Space Network, is that it impacted, and the impact actually signaled the accelerometers that the burn was done, and the thrusters stopped at that point. So if you saw the video, the animation, it's pretty much like the animation. It came down and bounced a little bit. I have a plot, but it won't show on TV, that for about 30 seconds there was confusion in the signal, and then it settles out at a nice steady signal on the ground. So 30-second transition after it impacted, and then everything was quiet. And indications from the spacecraft team is that it's sitting pretty much like a tripod like this, possibly on a sloped surface, because we can tell we're getting a fairly strong signal from the antenna pattern that we're pointing pretty much toward the Earth. And of course the camera and the XGRS, or the gamma ray instrument, are pointing toward the ground in this attitude.
Yes.
Seth Borenstein, Knight Ridder Newspapers. You talked about a factor of 10 in terms of composition detail that you can get by the 10 day, in these next 10 days. Can you give us a little bit of a primer on what the composition is, what your current knowledge is, and what that factor of 10? I mean, are we talking about 1%, going from knowing something, from 10 to 11%, or?
I can give you some outline, and here I have a quote from some material actually that the science team presented, and there are members of the science team here who can give you more detail or correct me if I'm wrong. The gamma ray spectrometer, of course, operated during the orbital phase. Let me back up to my opening statement. I said we know there are families of asteroids, and similarly there are families of meteorites, and it's a reasonable hypothesis that meteorites are fragments of asteroids, and we can look at them as samples that we can analyze in great detail. And the trick now is to connect meteorites with asteroids, families of meteorites with families of asteroids. Working hypothesis is that Eros is something called an LL chondrite, and that it's like that its bulk composition is like an LL chondrite asteroid. That leads to some expectations about certain elemental abundances, particularly abundances of potassium and iron. The orbital data don't clearly show those. Now that we have the spacecraft on the surface, the gamma ray spectrometer is almost in contact with the surface. We expect to get much better signal, and over 10 days should be able to determine one way or the other. If the abundances of iron and potassium are truly low in Eros compared to an LL chondrite, that tells us something. On the other hand, if we, over the next 10 days, we detect the signatures of iron and potassium, that tells us something else, that we verified that this thing is a member of a certain family.
I guess what I'm looking for is some kind of number, like you say, truly low iron content. Are we talking, 5%, and you're hoping to find out if it's 5%, whereas it looks like 10% from
I think we have to refer this to Dr. Tromka.
The difference is looking at whether it is about half of the iron composition that we would expect from a normal chondritic L or LL type asteroid. Our statistical accuracy, we're seeing levels that are consistent with this, but now we're down to the point where the statistical variance has to be much smaller to determine that difference, whether it is within 10% of what we expect, within the 10% tile of iron, for instance, or whether it is half that value. Our statistical error from orbit is not good enough to be able to tell that. The other very interesting phenomena is a possible depletion of volatile materials, which makes it somewhat different than the normal chondritic materials that we see. Whether this volatile, this depletion is real or not, we seem to see it with the X-ray. The potassium is also volatile. In X-ray we use sulfur, gamma ray we use potassium. Potassium is a similar sort of volatile material. To see whether that depletion is there is important. Now realize that the X-ray measures the first 100 micron depth, so we are only seeing the dust that is confounding us all. Now, is the dust like the subsurface? And that's what the difference between the gamma ray and the X-ray is telling us. So the gamma ray gives us the bulk composition down to about 10 centimeters below the surface. And so in terms of some of the questions that Dr. Ververka is asking is very important, because is this dust that we're seeing, which may be a global effect, different than the subsurface material? And again, we need a statistical accuracy much greater than we can ever do from orbit to do that. And from our calculations now, because of the signal to noise improvement and because of the decrease in the background due to the cosmic ray flux being reduced because of shielding of the planet, our signal, our accuracy can almost go up by an order of magnitude, which now gets us down to the statistical variances, which looks at these very subtle changes.
Warren?
Warren Leary, New York Times. A couple of hardware questions. Are you getting all your communications on the high gain antenna now? Have you polled the spacecraft to see if all the instruments are working, including the solar panels, if all of them are working or just some of them? And also there was some discussion earlier about turning on the magnetometer to look for magnetic variations. Are you still going to do that during this extra science period?
Okay, a lot of questions here. Let me see if I can remember all the answers. We're not on the high gain antenna right now. We're on the low gain, forward low gain antenna is where we're getting our information. We're going to try to do something on the fan beam this afternoon, I understand, as a test. But forward low gain is our primary antenna, and so we can't do too much through that. We're getting plenty of power into the spacecraft. We've been getting 80% of the power has been shunted off, actually. So we have all kinds of power. We have turned on the imager, and we've got confirmation that it's on. It's not taking any images, but it's on. And we are now in the process of turning on the gamma ray spectrometer, and we've got confirmation that part of it is on, and we're waiting for the high voltage confirmation. That might come in the next couple hours, we hope. Does that answer all your questions, or was there another one?
Are you going to turn on all the instruments?
The magnetometer, no, I don't think we're going to turn it on, but maybe Andy Cheng can comment on that as to what the status of the magnetometer, as to whether they're going to measure anything or not.
Well, the magnetometer was operated during the descent, and all the way down to 120 or so meters of the surface did not detect any signal that could be attributed to the asteroid. So at this time, we do not have a plan to turn on the magnetometer or to attempt to take more magnetometer data, because in order to have a useful measurement, we would need to have the instrument on for at least a few asteroid rotations, which means taking data over a, roughly a 10-hour span. And that creates a volume of data that's difficult to deal with given the current constraint that we have only a low data, 10 bit per second return from the spacecraft. So our plan now is not to attempt to get more magnetometer data. But the primary objective, in fact, is what Jack described, and that is to improve our measurement of the composition of the surface.
Do we have any other questions in the auditorium? Paul? Christy, Paul up front here. No, all the way on front.
After the Eros rotates and puts the spacecraft back into the sun, I realize it's going to go into darkness in April. Do you anticipate that you'll be able to revive the spacecraft at that time? And when is that apt to happen?
Well, that's quite a ways. That might be a whole year at the very least. I mean, I don't know the exact number right now, but I would expect it's been in cold soak for an awful long time. The hydrazine is probably going to freeze and so forth, and some of the lines might be ruptured, but we don't need that anyway. But there's a lot of things that could be broken with that kind of...
That was not one of our thermal design conditions.
I don't know if they're going to give us an extended mission that far either, so that's another problem.
Okay, one other question. You said that you're getting 10 bits a second now.
Well, we can get 26.5 kilobits per second. When we're on the high gain, that's our highest data rate.
Yes.
This is some science questions for Dr. Vaverka, I guess, in the images. The last image, which shows those possible depressions, I was speaking to another scientist yesterday, Monday, I'm sorry, about those, and he said that conceivably could have just been jiggle as the spacecraft hit the ground, because it's all very close to the moment you got cut off, and it seems consistent. He said it'd be very dangerous to make any conclusions, and I'd like your comments on that.
Yeah, I would first of all suggest don't talk to that person again, but...
Well, we'll discuss, all right. And another question on what was you were getting inches, you say less than an inch on, at the very last picture. When you were in orbit, you got very close sometimes, when it's a couple of miles. What was the best resolution you could get before this?
Right. Let me actually, there are two questions, so let me take the last one first. It's an easy one. Before we did the touchdown descent, there were several so-called low-altitude flybys, and my recollection is that in the lowest ones, we came down to roughly 2 kilometers of the surface, okay? And at that point, the resolution would have been something like 30 centimeters, okay? So that's, 10 inches or 12 inches, a foot, okay? Whereas in this one, of course, we got down much lower, so that's the factor of 10 at least, okay? Let's get back to the depressions. Now recall what happens here, okay, is that it takes us, on the descent, it took us about half a minute to play back an image, okay? So the image that was transmitted as our last image, we only got, the 75%, and the Alpha Centaurians got the other 25. That particular image was taken when the spacecraft was 125 meters or 400 feet above the surface, okay? Now, the thrusting that we did, I don't think is capable of affecting the surface from that altitude, okay? And I think it would be an interesting physical problem to try to focus the effect to the scales that we actually see, okay? So I don't think that has anything to do with it, but it's still a mystery because, if this were a surface, such as the surface of Mars, the obvious explanation would be in these layers, there is some volatile material that escapes and collapses the layers, okay? On Eros, again, airless body, waterless body, we don't know what's happening, and it's a mystery.
Leonard.
Leonard A. with Space.com again. Just to make sure, I mean, clearly the camera is working, and it's pointed down, so I assume there's no chance of getting any image of any worth, or...
I think that's the quick answer. The camera, of course, was designed to take images from a large distance. We weren't quite sure on descent how long it would remain in focus. We now know that, surprisingly, it's in focus even at 125 meters. It certainly is completely out of focus if we're a foot off the surface. So no, there is no reason to take imaging data, and we considered the image that we showed you as our last image.
And just a quick thing on, at some point there was some hope that, or some discussion about potentially lifting off, and again, the situation for fuel on board was what, nil, or you don't have enough really to do anything like that. The value of doing that would have been
We have
not high.
no fuel on board, plus or minus 8 kilograms.
Before we take another question here, I would like to go to a caller on the phone from Bartol Research Institute. Caller, would you please state your name and your question?
Yes, I want to say, first of all, that the survival of the spacecraft is truly a very serendipitous event. And I'm particularly interested in any new scientific results that would be obtained from the gamma ray spectrometer or the magnetometer in connection with the physical properties of the bulk of the asteroid. Dr. Tromke has answered that the GRS will continue to operate, and that will improve substantially the statistics on the chemical composition which they can infer. But I was surprised that Dr. Chang has indicated that during the descent, data from the magnetometer show no signal associated with the asteroid, and as a result, they've decided not to turn it back on. sometime later. Is that really a prudent decision to make, or is the problem due to the magnetic contamination by signals from the spacecraft itself?
Andy Chang, I think you're going to take that one.
Yeah, hi, Norm. Actually, I think the issue really is that we have to be confident of being able to separate out the solar wind, which, as you know, is always variable, from any field any probably low-level field that you might detect on the asteroid. And that's why we think we need to have the fairly long time span. And it's just a question of the volume of the data that you would have to generate, and could we bring it back? The gamma ray measurement we're talking about is actually only a very small volume of data. That's why it makes it, that's again, we're very lucky that it's a very important measurement that does appear to have a reasonable chance of actually being acquired.
Caller, do you have a follow-up?
Well, I'm just surprised that it's the volume of data that is the problem in precluding any possible significant discovery that might be associated with a longer run of data, even if the interplanetary magnetic field does vary.
Well, thank you for your call and your
You're
question.
welcome. Thank you.
Who's up next? Christy, Mike? Oh, okay.
Seth Bornstein with Night Reader Newspapers. Bob, just to go through the, can you go through the process and the decision on not to attempt a relift off, as you, which was a possibility? What were the factors weighed on that versus what you chose to do, and was the team split, or was this sort of a unanimous decision?
It's fairly unanimous, I'd say, because, I mean, it just didn't make any sense. I mean, we have almost no fuel left. I mean, it could be zero, could have a little bit, but even if we got up, the time that it would take to lock on the high gain antenna is probably going to be all the time that we're up in the air, and not the air, but I mean up above the asteroid, and then we'd be hitting again, so we're probably not going to get anything. It'd be a nice engineering stunt, but that's about it.
Plus,
so we want to let the spacecraft, leave it at rest. It's perfectly happy now, and leave it there.
and you got to remember, this is still a scientific mission, and we thought there was much more bang for the buck letting the gamma ray instrument do its thing now.
Warren.
Warren Leary, New York Times again. For Dr. Veverka. On that second from the last image of the boulder that was split, it's a little unclear. What altitude was that taken?
Right, I wasn't actually tremendously clear. It wasn't the second to the last image, but I can get the number for you here. That's probably an altitude of something like 2 kilometers in that particular case. And I'll get you the number right here. Yeah, that's about right.
About 2. Also, do you have any initial impressions or discussion on what is going on there? Why is that thing split, and what's happening? What's your initial idea there?
Well, I perhaps misled you in attaching too much importance to the split boulder. It's a neat thing, and it's a neat thing, especially because of the low gravity on Eros, things fall very slowly. Okay, and so it just indicates that this clump of rock, when it came out, was very weak. I basically showed it to give you a scale for the spacecraft. What's intriguing about the surface is that the surface at these resolutions we see is covered by boulders, and apparently in many places by much finer debris. And one of the issues is, where does this stuff come from? One likely answer, it's ejecta from cratering events on Eros. There's also some clear indications in our images that material on Eros moves downhill. Okay. What is surprising in this area is that you don't see any very fresh craters. So since it's unlikely that things don't hit Eros, it says that this process of effacing small craters is very, very efficient. And we have surprises such as the one I mentioned, where some process appears to make these very flat areas in low-lying places. So the question is, first of all, what sorts out the apparently finer material? What moves it, okay? And what causes the layering, what causes the collapse. So there's a whole series of processes, including one which I didn't have a chance to mention, I should mention right now, is in some places we actually see the boulders apparently disintegrating in space. Right around the boulder, there's an apron of debris. And again, in a terrestrial environment, that would not be very surprising. On an airless body, it is surprising. You could think, sure, it's exposed to impacts, so things can hit the object. But most of that debris wouldn't just crumple down in the immediate vicinity. So there's something else going on. And I'll just mention one intriguing possibility. We're talking about temperature on Eros. The day on Eros is 5.25 hours. Okay, so every 2.5 hours, in some places, in some seasons, every 2.5 hours, you go into darkness and then daylight. So every 2.5 hours, you get heated up and cool down. And the thermal expansion, in this case, might be an efficient process. Okay, that's not something that's common on the Earth, but maybe that's what's going on. So we're facing a bunch of processes that we are not used to dealing with. Okay, and that's why we're going to have to be scratching our heads and thinking about them for quite a long time. And there's going to be a lot of controversy as to what these things are, obviously.
Paul, do you have a question? Christy up front again. I'm out of your field of view. Here you go.
You said every 2.5 hours that the light-dark cycle, you have heating and cooling. Can you put the upper and lower limits on that thermal conditions?
Sure. Where that number comes from, okay, is that since you're going around every 5.25 hours, if you were exactly in the equator and the sun was on the equator, that's what would happen. I mean, obviously the pole is tilted so that at some seasons like the one we're at, some places are in perpetual daylight, others are in perpetual darkness. So there's an approximate number, okay? I was just trying to indicate that that sort of thing happens. And the only analogy we have is people have tried these kinds of experiments in terrestrial laboratories, okay? And certainly on time scales of tens of years or years, that mechanism actually does disintegrate boulders. It's not dominant effect on the Earth, because on the Earth we have moisture in the atmosphere, so what actually does crack rocks is the fact that once you form a little crack, moisture tends to get in there, and that freezes to form ice, and so on the Earth that's the main process and not the thermal expansion, but it works. Oh, the temperature variation, is that what you're asking? Yeah, well, again, depends where you are, what season, but it would not be unusual to be at a place on Eros, okay, where the temperature can change over that short time scale by 100 degrees, okay, or actually a little bit more. But, that's a significant change, okay, 100 to 120 degrees. Celsius, yeah. Again, okay, as an example, okay, because it depends on a lot of things, but an example would be a temperature that's a little bit warmer than the temperature in this room as a maximum, okay, there are such places and such times on Eros, to 120 degrees lower, okay, so you're going from, in Celsius degrees, from something like 30 degrees Celsius, down to 100 below Celsius, okay, so that's a very significant change, okay. And again, it's just simply because you're an airless body, so there's no cushion of atmosphere to moderate temperature changes.
Bob Zimmerman again. During the landing sequence, Dr. Zverok, you and Mark Robinson were looking at the images, and at one point you said it looked like you even saw what you called ghost craters that were maybe covered over. I even have a quote on my tape of you saying it looks like it's completely covered. Mm-hmm. Is that still a possibility? The small craters are there, but you're seeing hints of them buried under regolith?
Right. What Mark and I were commenting on is that in some of the early views on descent, there were indications of craters on a scale of 50 meters or 30 meters that we could see the outlines of, okay, but were very subdued. They weren't deep anymore. They were kind of hard to see, okay. So we referred to them as ghost craters, okay. And at least Mark and I, in looking at these images, we felt that what had happened in this area, at least one of the things that had happened, is that ejecta had come in from a different area, covered up previous craters, okay. And so if that really does occur, then what you might expect, of course, is if you're a big crater, big here is 50 meters, ejecta comes in, layer this big, it subdues that crater. But if you're a small crater, it completely fills you and obliterates you. So you lose the smallest craters, okay? I'm not claiming we know that is the answer. I mean, we know that there are subdued craters here. We also know, amazingly, that as you saw, there are no small fresh craters, okay? And so one hypothesis, which I personally think is unlikely, is it's not being hit by anything to produce small craters, okay? I don't believe that, okay? So that to me says there is something very efficient that if you're a small crater, you don't last long enough, to be caught by a glimpse such as we've obtained.
Do we have any other questions? Yes, up front.
Seth Borenstein again. Could the heating and cooling have anything to do with those depressions that you see? Or if not, and it's not obviously water escaping or volatiles escaping, what other possibility, I know you've only had 2 days, but what other possibility could it be?
Okay, allow me to answer in 2 parts. So first of all, a disclaimer. I mentioned the thermal cracking as a possibility, okay? At this point, I can't, I'm not being coy and cute when I sit up here and say that we don't understand some of these things, okay? So that is a possibility, okay? I am not claiming that we know that it is the likely mechanism, okay? So as long as we understand that, I will then similarly answer the second question. What do we know about the flat areas, okay? We know that they are flat. From what we have seen, they seem to prefer low-lying areas, okay? We know that they are layered, apparently, because we, in fact, see these collapse, and I didn't mention, in some cases, on the edges of these areas, we actually see things that look like concentric rings, which again suggests, some layering. Those are observations, okay? We are guessing, some of us are guessing that the likely explanation is that we're dealing with very fine, very loose material. Okay, I emphasize we don't know that, okay? We definitely, the features that we see that are the negative features are collapse features. There's in my mind, there's no question that, because on similar scales, we can see that in terrestrial cases where support has been removed. So we think fine material, okay, evidence of layering, something removes support, okay? That could be some process that suddenly compacts a loose layer below it or removes something from below, okay? If it were Mars, okay, I would immediately say there's ice on the surface and the ice melts and goes away or evaporates, okay? But there is no evidence that there is ice here. So I truly don't know what is going on, okay? And I have asked my team members, and no one has come forward with an explanation. So it's a mystery.
We have time for a few more questions, and if you have another one, Bob?
Okay, getting back to the landing period again. Right afterward, you were getting, when we had an impromptu press conference, Dr. Farquhar, you said 25 minutes later you were still getting data back from the spacecraft. Was that then from the high gain antenna? And I have a follow-up.
No, that was the low gain antenna once again, and we were getting a beacon back at that time, and we ultimately got 1 frame of data of telemetry. We didn't get any more than that until today. We got quite a few frames, and now we're getting pretty steady 10 bits per second.
All right, and just final question. During the period you were in orbit, I want to get some kind of scale. You know you were between 1.5 and 1.8 meters per second at landing. What was an average speed relative to the surface of the planet when you were, the asteroid, when you were in orbit? I know it changed because you were going in and out, but some sense of range, how it changed, the speed change.
Well, see, the orbital velocity was around 5 meters per second, but we were going in the opposite direction of the rotation. I don't know, so my nav team have that on the tip of their tongue.
The minimum speed in orbit, I looked through the entire orbit phase, is 0.94 meters per second, and the maximum speed was about 6.9 to 7 meters per second.
Relative
so like 2 to 15 miles per hour.
Okay.
Please use the microphone, or the viewing audience won't be able to hear this.
Sorry. Just reminding us that if we had not done the braking maneuvers, we would have impacted the surface much faster, or what, I don't know, 10 or was it 20 meters per second or something like that?
Yeah, roughly around 10 meters per second.
Leonard?
Leonard David with Space.com again. Maybe for Dr. Bergstrahl. As far as logistics of DSN time, do you have to borrow some time from other spacecraft missions? What's the aggregate total? Who would you be borrowing from? And what kind of cost number do you ascribe to the 10 days?
Haven't even looked into that yet, but I can't imagine not doing this. This takes 70-meter antenna time. That's the most expensive available. And not all of our missions require 70-meter. So I'm not sure what the competition is, but I think that this is doable on an every other day or every third day basis.
And cost extension, I know this money's coming from the project itself, or?
The project has some reserve. They haven't presented us with an estimate yet.
Okay, Paul, I believe you have a question, or is it answered?
Well, you may have just covered this, but Dr. Weiler told us Monday that the project returned $3 million to NASA. Will that $3 million adequately cover these 10 days?
As I say, we haven't seen an estimate, never mind the bill.
I don't think they put it in escrow for us.
I think we ought to move on to another question.
Are there any other questions? Okay, then before we conclude today, I'd like to tell the viewing audience, media, to stay tuned because all of today's visuals will be fed immediately following the briefing. They'll also be posted on the Near website at near.jhuapl.edu. And this concludes today's press briefing. Thank you all for coming.